very high melting point because it exists as a giant covalent polymer in both solid and liquid state. The stability of the +1 oxidation state increases in the sequence aluminium, gallium, indium and tellurium. Boron atom in BX3 has 6 electrons in the outermost orbital, and thus it can accept a pair of electrons from a donor molecule like NH2 to complete its octet. Hello everyone, this is Harshita Bhavasar from Vidhyaashram, PU College, Temple of Excellence. Today we are doing session 2 from the chapter Some P Block Elements. In the last session, we have discussed about general introduction and group 13 elements and also properties of boron family elements, that is group 13. In today's session, we will discuss about physical and chemical properties of group 13, anomalous behavior of boron and also important compounds of boron. We will see now first physical properties of group 13 elements. Boron has very high melting point because it exists as a giant covalent polymer in both solid and liquid state. The boron element is having high melting point because it will exist as very large molecule. Giant molecule means very large molecule both in solid state as well as liquid state. A regular increasing trend in density down the group is due to the increase in atomic size or atomic mass, which overweighs the increase in atomic size. As we go down the group in the periodic table, we know that atomic size will increases, gradual increases. So what will happen? A regular increasing trend in atomic mass also can be expected. Melting points do not vary regularly and decrease from boron to gallium and then increases. Melting point usually it has to increase, but some exceptional is there. It will not vary regularly. So it will decrease from boron to gallium and then increase. Low melting point of gallium is due to the fact that it consists of gallium 2 molecule. It exists as liquid up to 2000 degrees Celsius and hence used in high temperature thermometry. Here, low melting point of gallium is due to the fact that it consists of gallium 2 molecule. So, it exists in liquid state up to 2000 degrees Celsius. Boiling point of these elements shows a regular decrease down the group. Down the group, the decrease in boiling point can be observed. Next is chemical properties of group 13 elements, oxidation states and trends in chemical reactivity. First of all, we know that there are a various of oxidation states can be seen in P block elements. The atoms of these elements have 3 valence electrons, 2 in S subshell and 1 in P subshell. See here, 2 in S and 1 in P subshell. Therefore, all these 3 elements can show maximum of +3 oxidation state. The common oxidation states observed for group 13 elements are +3 and +1 except boron and aluminium. The usual oxidation state in group 13 are +3 and +1. The stability of the +1 oxidation state increases in the sequence aluminium, gallium, indium and tellurium. Here element boron, aluminium, gallium, indium and tellurium. Oxidation state +3, +3, +3 and +1, and it will gradually increases +3, +1 and +3 and +1. Here you can observe both the oxidation state. Except boron and aluminium, the outer elements also show +1 oxidation state. The +1 oxidation state becomes more stable as one moves down the group from the boron to thallium due to inert pair effect. Okay, except boron and aluminium, these are having some exceptions. The other elements also show +1 oxidation state. The +1 oxidation state becomes more stable as one moves down the group. In case of last element thallium, +1 oxidation state has been found to be more stable than +3 oxidation state. In case of thallium only, the +1 oxidation state has become found to more stable than +3 oxidation state. This is because after the removal of one electron from p block orbital, the remaining NH2 electrons behave like stable noble gas and do not take part in bond formation. Why it will show in the thallium means because after removal of one electron from the valence shell, it will act as it is obtaining complete or noble gas configuration. So, +1 is more stable than +3. The oxidation state +1 is more ionic than +3 oxidation state. In trivalent state, around the central atom, only 6 electrons are present in their compounds. Here, the +1 oxidation state is more ionic than +3. In trivalent compound, what is happening? The central atom should have only 6 electrons, but it is more in another compounds. So, one pair of electrons is deficient and hence they have tendency to accept a pair of electrons to achieve a stable electronic configuration. It will act as Lewis acids, the electron acceptors. In trivalent state, most of the compounds are covalent and hence they hydrolyzed easily. The boron trihalides are covalent in nature and exist as monomeric molecule having planar triangular geometry. Boron trihalides means BX3, 3 halogen molecules will be there, are covalent in nature and exist as monomeric molecules. Monomeric means like this. It is boron trihalide. It is having monomeric in structure and planar triangular geometry. B will be like this. Like this will be there. In these halides, boron exists in sp2 hybrid state and 3 BX bonds are formed by axial overlap of sp hybrid orbitals and boron of p orbital of halogen. It will be having sp2 hybrid state. Here one question. Aluminium forms trivalent ion, that is Al3+, but not boron. Why? Due to small size of boron, boron is present in very first period. So, what will happen? Very top of the group, it is having small size. As we go down the group, size will increase. The sum of its first 3 ionization enthalpies is very high. The first, second and the third ionization enthalpy, the overall sum of first 3 ionization enthalpy is very high. This prevents it to form +3 ions and forces it to form only covalent compounds. So, boron, what will happen? It will form only covalent compounds. But as we move from boron to aluminium, the sum of first 3 ionization enthalpies of aluminium considerably decreases and it is therefore able to form Al3+ ions. Boron is in top of the group in the group 13 elements. So, it is having very small size. So, it cannot remove 3 + 3 ions from its valence shell. So, it is having the sum of 3 first ionization enthalpy is very high. As we move down the group to aluminium, the enthalpies will keep on decreasing. So, it is able to remove +3 electrons from it. So, it will form aluminium +3 ions. This is the reason why aluminium forms trivalent ions but not boron. Next, reactivity towards halogens. All the group 13 elements form the trihalides, that is MX3, but by combining with halogens except thallium. See here, any element react with halogen to form MX3 trihalides. Due to small size and high electronegativity of boron, all boron halides are covalent and Lewis acids. This is very important point. Due to small size and high electronegativity of boron, it will form all the covalent and Lewis acids. These exist as monomeric molecules having planar triangular geometry with sp2 hybridization. All boron trihalides except BF3 are hydrolyzed to form boric acid. Except BF3, all halides with boron will form boric acid. See here, BX3 boron trihalide get hydrolyzed with water. It will form boric acid plus hydrogen halide. Boron atom in BX3 has 6 electrons in the outermost orbital and thus it can accept a pair of electrons from a donor molecule like NH2 to complete its octet. What they are telling? In the BX3 it has 6 electrons in the outermost orbital. So, it can able to accept a pair of electrons from a donor molecule like NH2. What will be happening? It will be accepting the electrons Hence, boron halides act very efficient Lewis acids. Once again, I am repeating, Lewis acids are electron acceptors. How it will be electron acceptors with respect to boron halides? Boron trihalides, in its outermost shell having only 6 electrons, it is able to accept one pair of electron from the donor atom. By that, it will be efficient Lewis acid. The relative Lewis acid character of boron trihalide is found to be obey the order Bi3 and boron bromide, boron chloride and boron fluoride. The halides of group 13 elements have halogen bridge dimeric structure as shown below for aluminium chloride, which exists as aluminium hexachloride. Group 13 elements with halogens, it will form dimeric, except boron, which will form monomeric structure. In the dimeric structure, each aluminium atom accepts a lone pair of electrons. Atom completes it from the chlorine atom bonded to the other aluminium atom. In doing so, each aluminium octet. See here, aluminium will form with 3 chlorine atoms, Al2Cl6. In the trivalent state, most of the compounds being covalent are hydrolyzed in water. For example, the trichlorides on hydrolysis in water form tetrahedral species. The hybridization state of element is sp3. Okay, here tetrahedral form will form. The hydrolysis of aluminium chloride in acidified aqueous solution forms octahedral. After the hydrolysis of aluminium chloride in acidified aqueous solution, it will form octahedral structure. In this complex ion, the 3d orbitals of aluminium are involved and the hybridization state of aluminium is sp3d2. After getting hydrolyzed from tetrahedral to octahedral, there is an involvement of d orbital. So, it will form sp3d2 hybridization. Next, reactivity towards air. Boron does not react with air in crystalline form. When boron is in crystalline form, it will not react with air. Amorphous boron on heating in air forms boron trioxide. See here, when it turns to amorphous boron, then it will react with oxygen in the enormous heat. It will form boron trioxide. Aluminium reacts with air to form thin oxide layer on the surface, which protects the metal from the further attack. This is called passivity. Aluminium will react with air or oxygen to form an oxide layer which protect or which avoid that another metal should not react with air. Aluminium form Al2O3 aluminium oxide on heating with air. Group 13 elements react with dinitrogen at high temperature to form nitrides. When it is treating with oxygen, it will form oxides. When it is treating with nitrogen, it will form nitrides. E will represent the element group 13. Nitrogen, it will form metal nitrates. Okay. See here, boron, aluminium, gallium, indium and thallium. Boron trioxide is acidic and reacts with basic metallic oxides forming metal borates. Aluminium oxide and gallium oxides are amphoteric in nature. Indium and thallium oxides are basic in nature. Here you can see all the kinds of oxides. Boron trioxide will form acidic in nature. Aluminium and gallium oxides will form amphoteric in nature. Indium and thallium oxides are basic in nature. Amphoteric means those oxides will be acting as both acidic and basic nature. Within group 13, acidic nature of their oxides decreases down the group. Okay, in group 13, acidity will decreases down the group. Reactivity towards acids and alkalines. Boron does not react with acids and alkalis even at moderate temperature. But aluminium dissolves in mineral acids and aqueous alkalis and shows amphoteric character. Boron will not react with acid as well as base. But aluminium dissolves in mineral acids and aqueous alkalis to form amphoteric character. Reaction of aluminium with acids. Aluminium dissolves in dilute HCl and liberates dihydrogen. See here, aluminium reacting with hydrochloric acid, it will form aluminium and chloride, also hydrogen gas. But concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. We have already told aluminium will form a protective layer or an oxide layer. Here you can observe. Then action of alkalis. Aluminium react with aqueous alkali to form sodium tetrahydroxyaluminate and liberates dihydrogen. Aluminium reacting with strong base, that is sodium hydroxide, and in aqueous means water will be there. Sodium tetrahydroxyaluminate will form with the liberation of hydrogen gas. Next, anomalous behavior of boron. In all the reactions you have seen, except boron, it will not act like that. So why it will happen? Boron, the first member of group 13, shows anomalous behavior due to extremely low size, high nuclear charge size ratio, high electronegativity and non-availability of d electrons. Due to these 4 reasons, boron shows little bit anomalous behavior comparative to other elements in group 13. The main points of differences: boron is typical non-metal, whereas other metals are metals. Boron is completely typical non-metal, whereas other elements metallic in nature. Boron is a bad conductor of electricity, whereas other metals are good conductors of electricity. Boron shows allotropy and exists in 2 forms, crystalline and amorphous. Aluminium is a soft metal and does not exist in different allotropes or different forms. Like other non-metals, the melting point and boiling point of boron are much higher than those of other elements of group 13. Boron forms only covalent compounds, whereas aluminium and other elements of group 13 will form even some of the ionic compounds. Boron only will form covalent compounds. The hydroxides and oxides of boron are acidic in nature, whereas those of other are amphoteric and basic in nature. The trihalides of boron exist as monomers. On the other hand, aluminium halides exist as dimers. Dilute acids have no action on boron, but others liberate hydrogen gas from them. Boron exhibits maximum covalency of 4 due to non-availability of d orbitals, while other members exhibit a maximum covalency of 6 due to availability of d orbitals. Example, aluminium will form octahedral structure, whereas boron will form tetrahedral structure or trigonal planar structure will also form. These are the points which shows the anomalous behavior of boron. Next, important compounds of boron. From the boron, what are the important compounds which we'll use commercially in our life? Borax. The correct way of writing the structure of borax is here Na2B4, O5OH4, 8 hydrate molecules due to tetranuclear units. Borax is a white crystalline solid. What are its properties? Its aqueous solution is alkaline due to hydrolysis. Due to hydrolysis, the overall aqueous solution is alkaline in nature. On heating, borax loses its water of crystallization and swells up to form a fluffy mass. On further heating, it melts to give clear liquid which solidifies to a transparent glassy bead consisting of sodium metaborate and boric anhydride. First, it will form in aqueous solution, it will form alkaline in nature. On heating, it will lose its water content and swells up to fluffy mass. On further heating, it will completely melt like a transparent glass and it will form sodium metaborate and sodium anhydride. See here, after complete heating, what will borax bead will form. Borax bead test. Borax bead is a mixture of sodium borate and boron hydrate. On heating, combines readily with a number of colored transition metal oxides such as cobalt, nickel, chromium, copper, manganese, etc. to form the corresponding metaborates which possess characteristic colors. By these elements, it will form characteristic colors. For example, when borax is heated in a Bunsen burner flame, cobalt oxide on a loop of platinum wire, a blue colored cobalt borate bead is formed. This is how the borax bead test will be done and it will be tested. Next, orthoboric acid H3BO3. Orthoboric acid is a white crystalline solid with soapy touch. It is sparingly soluble in water but highly soluble in hot water. In normal water, it will be sparingly soluble. In hot water, it will be completely soluble. Boric acid can be prepared by reacting borax with a mineral acid such as hydrochloric acid. Borax treating with hydrochloric acid, orthoboric acid will be formed and NaCl and water will be liberated. Properties of boric acid. Boric acid is a Lewis acid which interacts with water molecules to form the tetrahydroxyborate ion. Action of heat. When heated above 170 degrees Celsius, it dehydrates, forming a metaboric acid. What will happen when boric acid is heated at 170 degree Celsius? It will dehydrate. The water molecule will be removed. It will form metaboric acid. Metaboric acid melts at 236 degrees Celsius and when heated above 300 degrees Celsius, further dehydration. It can be further dehydrated at 236 degrees Celsius. It will form tetraboric acid. Further heating will form boron trioxide will form. Crystalline structure of boric acid consisting of layers of boric acid molecules held together by hydrogen bonds. The distance between two adjacent layers is 318 picometer. This is overall crystalline structure of boric acid by the formation of hydrogen bonds. Next, boric acid is considered as weak acid because it is not able to release hydrogen ions on its own. But it receives OH minus ion but it receives OH ions from water molecule to complete its octet and in turn releases H ions. Usually acids, the strong acids means it has to release H plus ions without the influence of any other reagents. But boric acid, with the influence of water, it will release, so it will be considered as weak acid. This is about the important compounds of boron. In the next session, we will discuss about diboron, uses of boron and aluminium and its compounds, and carbon family elements and its properties will discuss. I hope you have understood completely whatever I have taught today. So, we will meet in the next session. Thank you.